record. As you can see,
Thank you very much.
I tend to forget the same things, including making a stop in the middle of the lecture. So please, why don't we give me a ring when it's 16:45? Actually, I set an alarm. Well, I don't have my cell phone here, but give me a ring when it's about 45, and then we take a 5 minutes break to avoid you boiling at the screen. Okay. In the last lecture, we were discussing the renormalization group, and I'm just reviewing these basic concepts. And the concept underneath everything we said is that in order to have a solid physics description, you need a gap between two theories, and you have between two scales where you have some infrared physics and some ultraviolet physics. And as long as there is a gap between these two regions of the theory, what I'm plotting here is the spectral density, for instance, as a function of the energy. As long as I put my cutoff in the gap, then by just tilting very slightly within the cutoff, the parameters, the cutoff of my theory, this change can be reabsorbed by reshuffling my coefficients, which I denote like a set of coefficients, into a new set of coefficients. The parentheses here, the curly parentheses, just denote the fact that you may have a set of coefficients in your theory. So any change of resolution or cutoff can be reabsorbed by fine-tuning and renormalization of your parameters, by retuning of the parameters, which means that if you have a gap, you don't have a single theory for your physical system. You have a family of theories. Equivalent descriptions. And the word equivalent is crucial because it means that something is unchanged under resolution. And this is the origin of the word group in the word renormalization group theory. We shall see at the end of this course, when we will be dealing with Wilson's renormalization group in field theory, that this is not really a group, is actually a semi-group. But never mind what it is. As long as we are concerned at the beginning of this course, it's a set of invariances, an invariance under change of the cutoff of the theory. Clearly, this doesn't work forever, because when lambda becomes close, critically close, I put a lambda second, of the order of the typical energy of the UV physics, then my theory simply doesn't work anymore, no matter how much pain I take into retweeting the parameters. Now, stated in a different way, we have I like giving examples in different cases. We have nuclear physics, and then we have hadronic physics, or QCD, the physics of quarks and gluons. Now, when you get to the GeV scale, roughly speaking, there's no way you can tilt the parameters of a nuclear potential to reproduce the data, because your cross-section will be sensitive to the mergers of quarks. Your experimental data will know that there are quarks and gluons in your systems. And you cannot simply, hope to generate that physics by tilting the parameter of a nuclear potential. For instance, if you look at the cross-section for E plus, E minus production, right, articulation into photons and, into anything, then you typically see that, you get your cross-section, and then all of a sudden, roughly speaking, the GV, you start seeing a change in the cross-section, which is normally associated with the evidence for quarks or evidence for color. And clearly, there's no way this is omega. There's no way you can see that by changing the parameters of the potential. Okay, I think we agree. The last thing I want to say about the renormalization group at the beginning of the course, we'll go back to it at the end of the course, is that you can represent this tilting, this family of theory, graphically. Well, let's do it. Suppose we condense all the C's in a multidimensional plane. So say what I'm saying here, this is the case in which you have only two parameters, but in general, you might have multiple dimensions here because your set of parameters of the theory might be larger than just two. I'm just using two, C1 and C2, simply because I want to draw things on a board. But you might think about the more complicated theory. Say at some cutoff, you have fitted this and obtained two values, C1, 0, and C2, 0, which corresponds to some lambda 0. And then you change from lambda 0 to lambda 1, you get a slightly different value, and so on and so forth. So basically, what you do by doing this, you generate a whole trajectories of equivalent theories. And typically, this trajectory at some point ends because the theory stops being equivalent. Typically, you're interested, if you look at this as a dynamical system, you're interested in the stability point of in the plane. So there are situations in which theories, which are very different, so they have very different parameters, they run with the changes of the cutoff to the same points. So in all these cases, all the theories that are equivalent up to renormalization group transformations are said to belong to the same equivalence classes. So the equivalent class is the set of theories that are equivalent up to a renormalization group transformation, that is up to a resetting of the parameters, which means that they basically represent the physical content at the variable, slightly different value of the ultraviolet cutoff. Now, the concept of equivalent class is extremely powerful because it enabled, as we shall probably see later on, to establish bridges between theories that have nothing in common. But I don't want to digress on this at this level because it would sound obscure to you. And I will probably come back to this after we revisit Landau's theory in the context of statistical free theory and renormalization group. And then we will see that you can build connections between theories that you don't expect to have anything in common, such as string theory and the two-dimensional Ising model, by means of the concept of equivalent class. And this is quite profound in theoretical physics. But this is just blah, blah, blah for the moment. I just wanted to close this summary of the previous lectures. Okay, if there are no further questions, I will move on in my course and start tackling the first real chapter of our course. So please interrupt me if you feel you would like to ask questions. Otherwise, I would like to open, so to say, a chapter of the course which concerns mathematics, mathematical tools. And in particular, I will be focusing with one fundamental tool called the functional calculus. And my pen died. Fantastic. Today is not the day, guys. I think it's quite clear that this is not the day. Okay, functional calculus. So what is functional calculus? Well, we're all familiar with the idea of function. A function is something that takes an input, a number, and spits a number. If for physicists, then for mathematicians, they have more general concept of functions and sets and blah, blah, blah. For us, in application to theoretical physics, we can be happy with this very intuitive idea of a function. A functional, it's something as a mathematical object that takes as input a function and spits a number. Okay, so a functional is something that takes an input, a function, and will give me a number. Say xi, so this will be a number, let's call it c, which belongs, well, we can think about the complex set of numbers, the real set of numbers, depends if the function is real or complex or whatever. Okay? Example, the norm. The L2 norm of a function, which is nothing but the integral from minus infinity to plus infinity, for instance, of the square modulus of the function. Well, of course, if the function is normalized, this functional is trivial because it acts on a set of functions which have all the same norms. But in general, this is not normalized. And this is a number. In this case, it's a positive number. Okay, fine. Once you have a concept of a function, of a functional, let's look at the second word, that is the calculus. We know what is calculus. Calculus is the branch of mathematics that deals with possibly small variation or sum of many small variations. So basically derivatives and integral. So just as we have a concept of derivative of a function with respect to a variable, so in general you have a function of many variables, and you have the concept of derivative, or we have a concept of integral with respect to that variable. Now we will analyze the concept of derivative with respect to a function of a functional. And we will consider the concept of integration over a function. So derivatives and integrals over the set of functions. So these are the tools that we want to explore. And we want to do that not so much from the point of view of a mathematician, but very much from the point of view of a physicist who takes the least mathematics that he needs, doesn't care about all the, decorations and, I like very much Feynman's attitude on mathematics. He knew quite a lot of mathematics, but he was not one of those guys that really want to be elegant in presenting things in a very nice, packed, rigorous form, because he felt that was obscuring the physical content of the theory. He was using mathematics as a tool to get to physics, and we will follow the same inspiration in this course. So rather than giving you formal definition of a form of functional integration and functional differentiation, we will introduce them by looking at physical problems. And today we'll look at the first physical problem, which will lead to the concept of Feynman path integrals. Which is a first example of functional integration. Okay? So let me ask you guys, have you already seen, how many of you have already seen Feynman path integral in their education? Known?
From Vanzo's course. Yep.
Huh? On Vanzo's course. Okay. How many of you? So this is 2 people out of the full bunch in the class, right? Am I correct?
Mm-hmm.
Only those who have taken advanced quantum field theory. Very good.
Maybe there is another one, but it's not in today's room. Yeah.
Very good. So I will assume you haven't, as I always do in this course. right? Uh, for those who have, you will be a little bit bored today, but you will. I think you should still pay attention because at some point we will draw a connection between Feynman's path integral and stochastic dynamics, and which you probably haven't seen, and this will sort of open an entirely new way of looking at the same problem. So I need a consistency within this discussion. So probably even if you have seen it already, pay attention. Okay, so what is Feynman path integral? Well, Feynman path integral is basically part of Feynman PhD thesis, which is embarrassing for everybody else in the world. If I look at my thesis and Feynman's thesis, really I need a doubly logarithmic scale to put them on the same plot. Because basically Feynman, during his PhD, developed QED, and he did that by introducing Feynman path integrals, which is kind of embarrassing. Anyway, what is the goal of Feynman? Feynman wants to reformulate quantum mechanics in terms of classical concepts. So that's the ultimate goal. He thinks that if you look at classical mechanics, there's a quantum leap between the classical formalism and the quantum mechanical formalism, meaning that you reached quantum mechanics, you talk in terms of paths. Classical mechanics have trajectories, phase space, and all that, and all of a sudden you throw that into the garbage, and you begin talking about operators, wave functions, and it's quite hard to understand how the two things can go from one to another, and how can you connect? How do you enter the quantum realm smoothly? I mean, physics is not all at one, right? At some point, you might be able to see some quantum effects and then a little bit more of quantum effects, and eventually you're dominated by quantum effects. But quantum mechanics is very obscure in explaining the transition from the classical realm to the quantum realm. You might say there are LFS theorems that show you that expectation values of operators or certain operators obey the classical equations of motions, but it's a result that is entirely based on a quantum formalism. So in Feynman's path integral, you reformulate the entire quantum mechanics in terms of trajectories. Of course, it cannot be just simple like one trajectory. Otherwise, you would be fighting against the uncertainty principle, as people who have seen the multiple slit experiments know very well, right? So eventually, we've got to sum over infinitely many trajectories. And I'm sure you all, I've done this discussion in my introductory course to quantum mechanics, but I guess you've all seen the multiple slit experiment in quantum mechanics. And as anybody in the room have never seen this experiment? Okay. And one of the important points is that you discover that while the particle retains particle behavior here at the final screen, you must conclude that the particle can go from either holes during the transport from the source to the screen. And if you repeat that and you put multiple screens in different positions, you're constantly drawn to the same conclusions, that basically you can go from here to here in multiple ways, and that the probability of making it here is the sum of all these amplitudes somehow. That was the intuition from the discussion of multiple slit experiments. So let's formalize this mathematically. We are interested in the wave function at time t. That's the goal of quantum mechanics, computing the wave function, right? Now, I will be dealing with one dimension for sake of simplicity. Anything that I say can be trivially generalized to multiple dimensions. Now, the wave function at time t is nothing but the projection of the quantum state at time t onto positions representation. And this can be written as an evolution operator in terms of the Hamiltonian as the wave function at time 0. This is the solution, if you want, of the Schrodinger equation. Because if you accept that, then clearly d by dt psi t I h bar is equal to h psi. Now, last step here is to say, fine, in here I stick a 1, and I reminded myself that 1 can be seen as the sum over all position eigenstates projections. So this is like when you take a vector and you take the inner product with respect to a complete basis, and you can say that my vector v is the sum of the inner product with all the bases times the basis. And that's the inner product, and that's times the basis. And that's the sum. I'm sure you've seen this before, but let me just summarize it when I see it. Now, okay, so this means that this can be written as dy x e to the negative I over h bar h t y psi naught. Therefore, I'm going to rewrite this in the following way. So this integral, represents the time evolution of a system where this function k is defined as the matrix element of the evolution operator in position representation. So basically it's the representation of the evolution operators in coordinate representation. And it's called the propagator, or Feynman propagator. Why is it called the propagator? Because these functions, through this integral, basically takes in input the wave function as some time 0 and propagates it forward in time by a time t to a later time. So if you're able to compute the propagator, then you have solved quantum mechanics. Why? Because, in quantum mechanics, time-dependent Schrodinger equation is an equation for the time evolution of the wave function. You give me an input, my boundary condition, my initial condition is the initial wave function, and I give you as output my final wave function. So here is an input. If this is equivalent to reducing to quadrature the problem solving quantum mechanics. Remember, reducing to quadrature, when you do electrostatics, you have this problem, which is a differential equation, Poisson equation, and you can solve it with the Green's function method. Right? You've seen this. The solution is, you physically interpret it as the contribution of the density. There's a 4 pi, I guess, here. I don't remember if there's a 4 pi or not. Never mind. So this is equivalent to this because this solves these equations. Right? So similarly, in our case, we have a differential equation. And we have a solution of the differential equation through the propagator, with an integral and a convolution as exactly like before. Okay, so really the question is how to compute the propagator. Okay? Now, let's do that. So our interest now is all into evaluating this quantity. And we do that in a number of steps. The first step is very trivial, but very powerful. We say T is equal to a sum over k from 1 to n minus 1 of delta t, where delta t is t over n. So what am I doing? I'm taking my time interval t and I'm splitting it into n intervals of size delta t. Okay, why should I do that? Well, we'll see in a moment. So if I do that, then of course this propagator will read sum over x e to the minus I over h bar delta t h plus plus delta t h, right? Now, in general, if I have two operators, a plus b, this is not equal to a to b, of course, if these are operators. However, corrections to this formula are functions of the commutators between a and b. So in other words, this is exactly true if a and b commute. Okay? But clearly, all these terms commute with one another because they are the same term. So, very much trivially, I can say sum over x e to the I over h bar delta th times e to the negative I over h bar delta th, and blah, 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 until I get the last one, and I get a y. Okay? So this is called the Trotter decomposition, by the way. It looks like so trivial that it's even not worth discussing, but it turns out that it's being used in so many approaches, especially numerical algorithms, that the Trotter decomposition is one of the milestones of computational quantum mechanics. Okay, given the Trotter decomposition, what we are actually doing is trading the difficulty of computing a highly nonlinear operator, the evolution operator in the Hamiltonian, with the difficulty of computing many very small operators, very small evolutions. And you see, to the point that we can choose delta t small at our taste at the price of introducing sufficiently many different steps. And why do we want to do this? Because remember, physics is the art of finding sensible approximations. And in order to find an approximation, you need something to be small with respect to something else. Now, by introducing a small scale delta t, now you can tweak your delta t in such a way that this quantity is much less than 1. Because you simply have to choose enough time steps for this to be rigorously true for any given accuracy. You want this to be 0.1, you introduce 1,000,000 steps. You want this to be 0.01, you introduce 10 million steps, and so on and so forth. Okay? Okay, so thanks to this possibility, we will be able to compute the propagator. How? Let's see. The first thing we want to do is to compute, to note that in between any of these time evolution operators here, I can always sandwich an identity. Of course. And again, what I'm going to do, I'm going to write each of these identity as a resolution. So for instance, this is going to be the last one that if I start counting from the right and I go to the left, this is going to be my nth minus 1 identity. So I will use a variable yn minus 1. And of course, the ones immediately after will be integral dy n minus 2. Today is not a day. This will be the integral in y minus 2, yn minus 2, yn minus 2, and so on and so forth. Okay? So, collecting all things together, this is a product of integrals of integrals, and multiplying a product of terms in the form now, with some caveat that the very first of these is actually equal to y, and the very last is equal to x. Okay, so now we have this pretty weird looking expression. How many of these integrals and of these products there are depends on n. And you know, if you do things, depending on how you count, typically you count from 1 to n minus 1. But in the end of the day, even if you miss one of these terms, you make an error of order delta t, which you assume is small scale, but the rest that is remaining finite, so it doesn't really matter. Okay, please stop me if I'm saying something that doesn't make sense to you. Otherwise, I would say, you know, now we are left with a problem of computing.
Sorry, am I the only one who lost the connection?
Yes.
Where did you lose my connection?
No, internet connection might not be stable. That should be my problem.
Well, but how long have you lost?
Oh no, just the end of the formula. Started writing the first differential, but I'm following it, no problem.
Okay, good. Okay, thank you for telling me. Okay, so what I want to emphasize now is that all we need to be able to compute is this object. Because if we can compute a general expression for this object, then you multiply all together and perform and evaluate the integrals, of course, formally, we will get a closed expression. And we will have reduced to quadrature the problem of computing the propagator. Okay? So let's focus on this. So now our goal is really computing an infinitesimal time evolution, no longer a finite time evolution. So the brilliance of all this is to find a way to reduce something that is, you know, it requires the full diagonalization of the Hamiltonian into something you can do. Because you see, if I have a finite time evolution here, say I was interested in computing this, but with a finite time evolution, I have no idea how to compute this matrix element. The only way I need to do is to know all the eigenvalues of H, that is, solve the entire quantum mechanical problem in terms of a quantum spectrum. And if you know that, then of course you can stick the identity here, this time in terms of the eigenvalues of the Hamiltonian, say here. And then in this case, if you know all the eigenvalues of the Hamiltonian, then obviously you get something familiar. Right? But now this can be replaced with En. And as a result of this, in the end of the day, this is a sum over e to the negative I over h bar the energies And then I have the wave function star k plus 1 at y, the nth wave function star at yk plus 1, multiplying the wave function at yk. So this calculation is simply telling you that if you want to keep this finite, then you really need to diagonalize the Hamiltonian and have all the spectrum, which is a formidable problem. There is a payoff in what we did so far if computing this for infinitesimal delta t is not that hard, doesn't require diagonalization. Okay, so let's do that. I'm switching color for no apparent reason. So let me switch now between potential and kinetic energy operators. Because precisely in this comes the brilliance of the entire approach. All right, something is not working well today. One thing that we can do here is to consider the fact that while these two operators don't commute, so in general, E over H bar T plus U delta T is not equal to e to the negative over H bar T delta T e to the negative I over H bar U delta T. However, corrections come, remember, with a commutator between the exponents, which in this case contains terms like this, right? The corrections here, okay? Now, clearly, these corrections are order delta t squared. That's the smart thing. So by the Trotter decomposition, the gain is that you can actually split these operators into two terms. And then basically this is the key to solve this problem. Why? Because you see, remember, we want to do this. That's our goal. Now, to do that, let me introduce, well, first of all, if I can do this, I can evaluate very simply this matrix element because the potential is diagonal in position representation, right? So I've replaced the operator here with the potential evaluated at yk, and I can take it out. And then I'm left with something that looks like this. Okay? Now, this is the last difficulty we need to bridge in order to complete the calculation. Because you see, this looks like an impossible task because this is not diagonal in position representation. However, here comes the trick. Let's change basis and switch to a basis in which the kinetic energy is diagonal. And that's, of course, the momentum representation basis. So the idea here is to write this as e to the negative delta t over h bar u of y of k. And then here I write the integral over dp over 2 pi. And of course, I can write pk if you want. And then I get like yk plus 1 e to the negative I delta t over h bar p squared over 2m. And then here I write pk, and then I get pk yk, right? Now, if I do that, and I continue up here, if I do that, I can now get something that looks very much familiar. It's going to be e to the negative I over delta t h bar u of k. And then I get this evaluated on this will give me my integral dpk over 2 pi. And this will give me a phase I over h bar p k y k, right? Because that's the projection between position and momentum representation, just a Fourier space phase. Then I will get e to the negative I delta t over h bar p squared over 2m. And then I will get this acting on this, which will be a phase with a different sign. So we get pk y yk minus 1. So guess what? This is an integral which almost looks like a Gaussian integral because it has a quadratic term here and a linear term here. So you can complete the square and make it Gaussian, right? The only difference is that there is an I here. However, it turns out that this integral can actually be calculated exactly. Now, you can use the Gauss formula or, to prove it because, in the end, it's the same idea that you use when you evaluate on the complex plane, the Gaussian integral. But I'm not concerned with that. I will just spit the result out. And the result, once you gather things together, you get a result that looks like this. Now, this term comes from here. And this term is the result of performing, let me use a different color. This term comes from integrating this part here. Okay? So just a little bit of mathematics, nothing really deep in here. But now we're ready to sum up and wrap up everything we've done so far. So what we discover, remember that our propagator, y, t, x, or maybe it was x, t, y. This propagator here was a series of integrals, which I now write explicitly, d1, dy, n minus 1. And then a product of propagators. Remember, yn minus 1, actually the last one was x. Then I was having like e delta t h over h bar yn minus 1 and blah, 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 right? Now, if you evaluate each of them according to what we just did, then you'll discover that this is simply a product of exponents. But a product of exponents of classical quantity now, numbers, no longer operators. Now it is really true, literally true, that the product of exponent is the exponent of the sum, because we have eliminated all operators. So now what happens is that we get terms like 1 over h bar, then we have a sum over k delta t, and then we have like yk plus 1 minus yk squared over 2m with a delta t squared here. Because there was a mistake that I'm about to correct, yk. So there was a mistake here. The result of these integrals, if you want, I can write it this way. The delta t was downstairs here. So in order to make it upstairs and collect out this delta t here, I need to divide a further delta t. Okay. Now, this equation doesn't look particularly inspiring if I look at it this way. But let me analyze it a little bit further, and you will immediately understand what it actually means. So let me clear the page if I can. Okay. So, and rewrite the object of our interest, which is the Feynman propagator. K of x, t, y. This was written as a series of integrals, d1, and the number of integrals and the number of time steps here depends on how much we chose to perform Trotter decomposition. Okay, so this is the probability from a particle that was in x at time 0 and happens to be at y at time t. So let me put on the x-axis the time, and on the y-axis the position. So let me call position and time. So this is t, and this is naught. At time naught, the system was in y. At the time t, the system is in x. Now, what this expression is telling me is that in order to compute the amplitude for this process, what I need to do is to consider a large quantity of intermediate times, and at each time, I should look at the intermediate position y. For instance, this is y1, y2. This is the position y2, which corresponds to the second term here. This is y3, y4, and so on and so forth. And I have to construct paths that connects all of these little pieces. For instance, this. To each of these paths, I associate a phase, which is given by the sum of k delta t, and let me not write whatever is inside here, okay? But I need to do this for every possible choice of y1, y2, y3, and so on, because I'm integrating over all the intermediate positions. So what this integral is doing is summing over all possible trajectories, connecting y at x discretized at the level delta t. And for each trajectory, you sum a contribution proportional to a phase, which is written here. So really, this is an integral over all possible ways. It's like if every single term here was a single slit experiment focused around the particular value of y that contributes to the integral, right? This is an n-dimensional integral, one values of y per each time slice. And it's like if any of these particular contribution to this integral was a trajectory that connects the sequences of these y's. And then I have to sum another trajectory where maybe I just vary one of these. And then I have to sum all. So this multidimensional integral is basically a sum over all possible trajectories that the particle can take in going from x to y in a time t. And for each of these trajectories, I associate a phase given by the exponent there. So in the limit in which delta t goes to infinity, and I will have to discuss this limit in a moment, then it means that I have infinitely many time slices, and therefore the formal limit of the product of integrals is represented as a notation in the following way. Now, of course, in this product, there's a delta function for the first term to be at y, and for the last term to be at x, right? If you want. Now, even my iPad is trying to abandon me. It's really a sign of destiny that these lectures is not supposed to go. Okay, so now instead of carrying around the delta functions, I've replaced the last and first with the extremes of the functional integral here, just to remind me that I'm starting from y and landing at x. And basically what this integral is doing is summing over all possible trajectories. Hence the name path integral. Okay? Let's now look at the second term here, the integrand. The integrand, let's analyze it. It's I over h bar, sum over k delta t. Now this clearly in the continuum limits will become an integral in dt from 0, dt prime from 0 to t. Now, what about these terms? Well, the second term is quite simple, is basically u evaluated at u at position t prime. Now, the first term, it's kind of a, it looks like it's a, you know, if you look at this, it looks like if you interpret x plus yk plus 1 minus yk divided by delta t as a velocity, it's a displacement over an infinitesimal time, right? Then if you were to do this, then this would be simply y dot square over 2m t prime, the instantaneous velocity of your particle, the instantaneous kinetic energy, sorry. However, this is a notation, not a mathematical definition. Can you see why? Why this is not really a kinetic energy? Why this is not really the Newtonian kinetic energy? Can anybody see this? Let me tell you, because you see, all of these trajectories, are these trajectories differentiable? Hello? Can this path be differentiable?
No.
No. By definition, they are segments. They're made of segments, right? So I'm not entitled to identify this with the time derivative in the sense of Newton, which is the time derivative of the smooth trajectory, right? The velocity is really the limit of a smooth Newtonian trajectory. So it's really an interpretation more than a, you know, you should be careful that I call this kinetic energy. I identify this with the kinetic energy, but in general, this is not a differentiable trajectory, okay? But if I do this, now, if I close my eyes to this mathematical little inconsistency to define a derivative of a non-continuous function, if I'm not worried about that for a moment, and I look at this with physics eyes rather than mathematics eyes, then what sits in the exponent is the time integral of the sum over kinetic energy negative potential energy, which you know from your education as a well-known name. It's called the Lagrangian. And the time integral of the Lagrangian is called the action. So basically, what we are doing here we are saying that for each trajectory in the path integral, I should associate a phase proportional to the action of that trajectory, where the action of the trajectory is really, what really the action is a discrete sum, which depends on how much I have discretized my system. But I look at it, and since I choose t that t very large, I identify this with y dot square over 2m u of y. Okay, so we came to these fundamental results of quantum mechanics that propagates throughout basically all of theoretical physics. We have a final expression for the propagator in terms of path integral, which in a compact form reads like this: the Feynman propagator, our ultimate goal from y to x in dy e to the I of h bar s. And the action is in fact a functional of the path. You see, I'm integrating over all path, which means I'm integrating over functions of time which obey the boundary condition y at 0 equals y and y at t equals x. And the integrand is a functional of the same path. So this is a functional integral. So this is the results of reducing the quadrature through quantum mechanics. Many, many things follow from this discussion, and we'll analyze them in the forthcoming lectures. But let me just say a couple of them. So let's make some observation. Well, the first observation we are making is that operators and wave functions or states have disappeared. Correct? So somehow, all the concepts that were significantly different in quantum mechanics with respect to classical mechanics are no longer present in the mathematical object, Feynman's propagator, that represent the key to solving quantum mechanics. So basically, you have represented quantum dynamics entirely in terms of classical quantities, or so-called C numbers. Now, C numbers is a kind of a fuzzy concept. As far as our course is concerned, C numbers means complex numbers. But for those who are, into quantum field theory, C numbers may be also different objects called Grassmann numbers. But forget about what I just said if you're not into high energy physics. Okay? So basically, as far as us is concerned, we have represented quantum mechanics with complex numbers, no longer operators. And this is crucial because, you see, due to this fact, we can now address the question, what happens as I slowly walk into the quantum realm from the classical realm? Because our theory now is formulated, I have a quantum regime of my theory. I have a classical regime somewhere here. And there is a fuzzy transition between the two. And what we were able to do in this calculation is to formulate this regime in a form that is not based on different mathematical concepts than the classical regime. So this should make it simple to understand what happens in between. How do you go from classical world to quantum world? Basically, how do you play Ant-Man? Okay? And that's the last thing I'm going to do today. So let's reanalyze my quantum propagator. Now, this is a sum of phases. Now, anytime you perform phases that are highly decorrelated, so you sum many complex numbers which are completely different, so you say it's quite immediate, basically based on central limit theorem, if you want, or any other argument like this. When you sum objects which have widely different phases, the sum on average averages to zero, because phases come with those signs, and it's basically the same problem as summing quantities for real and imaginary part, many quantities of variable sign. And the central limit theorem tells me if I sum a large number of quantities of variable signs and stochastically distributed, then I get zero on average, right? I get a Gaussian distribution. And the Gaussian distribution is performed around the average. And if the average is zero, I get zero, right? So most of the time, if I perform random phases, I will get zero in the sum because of destructive interference. So the hello, is anybody spoken? Any question? So in most paths do not really contribute because their actions or phases average to zero. But for this to be true, you have to assume that the phases are completely uncorrelated, right? Because only if you sum independent Gaussian numbers, you get zero on average, right? If the distribution of each Gaussian numbers is average from zero. However, there are exceptions. And the exceptions are when you have some very, very, very specific paths which have an important property. If you perturb this path by a little bit, the action basically doesn't change. Because you see, if you can find these paths such that in an entire neighborhood of the path, the action remains constant, well then, when you sum these paths, they will not destructively interfere, okay? Because they all have a coherent phase. So basically, what I'm saying is that only the path that contributes, which contributes to K, lie all in the vicinity, in the functional vicinity of those for which S is stationary. What does S stationary means? It means that if I look, it means that if I take S at some path Y, and I take a S at the path Y plus a small difference in the path. So let's say this is the path Y, and this is the new path Y plus delta Y. So that delta Y is really the difference between these two little paths that I drew. Well, this must be such that this difference between these two well, in general, this difference is of order delta Y, right? But in this specific case, is around some of this path, you assume this to be of order delta Y squared. In other words, you're assuming that basically changing S with respect to the path a little bit doesn't change the action. We're going to explore what this means mathematically a little bit more in detail next week, next lecture, when we'll discuss the functional differentiation in more rigorous mathematical terms. But as far as this lecture is concerned, I'm going to just stick with the idea that there are specific paths, just as in, when you have a function, there's an analogy. When you have a function, you look at the function as a function of its variable. And in general, in the vicinity of the point, the function changes linearly with the displacements, right? However, there are some special points, the stationary points, where the function changes only quadratically with the displacements. These are the stationary points of the function. Likewise, in the path integral, as far as the action is concerned, there are paths, special paths, such that the action as a function of this path does not change linearly with the path. So this means that if I take the integral from 0 to t of y dot square u of y of tau, and I impose the principle of stationarity, what do I get? Does anybody know? No? Are you connected? Is there anybody connected? Am I talking? Okay. Okay, so what I'm trying, okay, so I was planning to do this next week, but let's do it now. So let's evaluate this variation. How do I evaluate this variation? I take the action of y of tau, and I add a little bit of dy. Okay? Okay? And I want to compare this. Eventually, what I want to do is to compare this with the original action where I didn't do the variation. And then I want this, to be of order delta y squared, and see what happens. Okay? Okay, if I do this, let's look at this integral delta t y dot squared m to m plus, there would be a term delta y dot squared to m, but I can forget it because this is of order delta y squared, right? So I'm not really interested in this. This is small. I'm interested in the linear variation. I want to send anything proportional to delta y to 0, okay? That's how I impose stationarity. So the only terms proportional to delta y is actually delta y dot m, right? As far as this is concerned. And now here, I need to, expand this, and I have this is u of y plus the derivative with respect to y, and I cannot write here because of, okay, I need to go up here. So integral d tau y dot square to m plus delta y dot m negative. I take the derivative of u with respect to y, and then delta y negative u of y. Okay, so that's this term here. Now I need to take away this term. Okay, but if I do that, you see, I'm simply removing these pieces here, because this is the definition of y s of y. You see that? So basically this and this minus this disappear. So let me take them out because I'm interested in this difference. So everything together sums up. So what did we learn? We learned that the difference between s at my path plus a little bit of correction minus s of y is written as the integral in d time from 0 to t of dy dot y dot m negative du over dy. Let me write it as u prime because we are in one dimension after all, delta y. Now I integrate this term by parts, and I get integral d tau 0 to t of dy, and then I get y double m negative plus u prime here, right? Now I want this to be equal to 0 for all dy, because I want this difference not to be proportional of dy, delta y, but to be of order delta y squared, the terms that I've neglected. So all the terms proportional to delta y must be 0. Therefore, the only way this can be true if the argument is 0. So the result that we obtained finally is that these spatial paths, which represent the equivalence of the stationary point in normal calculus, but they are spatial functions for which the action is stationary, obey quite well-known differential equation. What differential equation is this? Newton's. Ha! We recover quantum classical mechanics from quantum mechanics. Do you see it? So basically, let's go back. So we discovered that the propagator from, say, y to x is obtained by summing all possible paths. Most of these paths have a random phase one relative to the other, so they basically all interfere out. However, in this place, there are some special paths which play the role of the stationary points in standard calculus, but they are stationary functional points. And here, in the vicinity of these points, the path actually constructively add rather than interfere, right? So basically, in the limit in which these fluctuations are small, and we have to discuss what limit is it. In other words, in the limit in which the phases decorrelate very fast, so that as soon as you move a little bit from the path, you get a random phase, then all of these complicated path integrals, which describes the dynamics of the system, can be well represented only by the functional vicinity of the classical path. So in the limit in which the variation of the action, so the typical actions are large in units of h bar, then as soon as I move a little bit away from this classical path, I start to interfere destructively, I get zero contribution. And in these limits, only the paths that are really part of the dynamics are those that obey Newton's equation. That's why we have Newton physics, because this, what we observe when we throw a ball against the wall and it bounces back, is just a narrow, very narrow bundle of paths in the path integral that don't interfere destructively, but constructively. All the other possibility for the ball going from where I'm sitting to New York and back to the ball to San Francisco and back, which is clearly not a classical path. It's possible, it's in the path integral, but it interferes destructively with any other path. And so I will never see that. However, whenever my system becomes small enough or my time interval becomes small enough so that the action of all these paths, they all are small in units of h bar, then all of my phases, in the path integrals are basically one, because this is now small, right? So when h bar is large, or of course h bar is what it is, cannot be large. What really is large is the action of my system in units of h bar. Then all paths begin to count. And the classical path has zero function or measure, it basically counts for nothing, and it describes nothing of what's going on. So this is the quantum realm. So basically where we're discovering is that here is quantum, and that's my last. This is classical. And the classical realm is based a's over h bar much bigger than 1, a's over h bar much smaller than 1. And now I have a continuum of transition, because in principle, as I move from classical to quantum, I have the semi-classical regime where I have only path of order delta s squared contributing. Then maybe I need to include also delta s fourth when I'm here, and so on and so forth, until when I'm really deeply quantum, I really any Taylor expansion of the action around the classical path loses any significance, just as much as if I have a complicated functions. I cannot hope to be expanding the value of the function here, as in order to obtain the function to in this point by a Taylor expansion around this point, I need very, very, very many points, right? I need a polynomial of order 1, 2, 3, 4, 5, 6, right? And of course, this becomes increasingly difficult. At some point, you have to sum them all. And that's what happens when you enter the full quantum realm. So in this lecture, we understood how mathematics can be inspiring. We started off from a purely mathematical statement. What happens if I want to represent quantum dynamics at the quadrature level? And we came up with a physical interpretation of the classical transition in terms of some overall possible histories of my system. Okay, I think I overtook your time. There was some delay today, so I needed to take this time. Hopefully, I will solve this problem before Thursday and we'll go back to normal. Okay, I wonder whether you can send me by WeTransfer the recording, so I will merge the first and the second part of the lecture and then put it on YouTube. Okay.
Okay.
But please remember, you can find this lecture in my YouTube channel already in a different, slightly different format, but it's the same content. So, and it's still me teaching it. So basically it's a parallel universe where I teach the same lecture. Okay.
Okay.
So next week, we're going to discuss a little bit about this. Next lecture. See you guys.
Professor, would you allow me to point out just few things in your notes? I believe that among page 9 and 10.
Okay,
Huh?
so why don't we do that on Thursday?
Next time. Okay.
My iPad
I'll try to
is
remember.
running out in seconds.
Okay.
I cannot do that. But on Thursday, we'll do that. Thank you for pointing
Fine,
this out.
fine. Okay.